powerful storms approach, or floodwaters rise, when a volcano threatens to blow, we turn to science and technology to warn us, to seek shelter or get out of the way. But can they face down the ultimate danger? A speeding projectile from the depths of space. Can new generation space missions neutralize the threat and save the planet from a killer asteroid? Welcome to the new age of planetary defense.
Liftoff of the Falcon 9 and DART on NASA's first planetary defense test to intentionally crash into an asteroid.
DART, the Double Asteroid Redirection Test, is a 610-kilogram spacecraft on a unique test mission to crash into an asteroid and knock it off course. Its target, an asteroid about the size of 2 soccer fields, called Dimorphos. Scientists have compared DART to a golf cart ramming into the Great Pyramid of Egypt. In this test mission, they expect to change the orbit of Dimorphos by only a fraction of 1%. But if an incoming asteroid is far enough away, that could be enough to deflect it away from Earth and avoid a catastrophic impact.
There are 2 things that make the impact hazard unique. First, it is in fact the biggest natural hazard we know of. Impact by an asteroid a mile or more in diameter could destroy 1 billion people, far beyond any other potential natural hazard. The good side is it is the one hazard that we think we could eliminate entirely. You could never stop an earthquake or a volcanic eruption, but if we had warning of an asteroid headed our way, then at least in principle, we have the technology to change its orbit, deflect it, and have it miss entirely.
And yet, we may not always have enough warning time. February 15th, 2013. The town of Chelyabinsk in southern Russia is just waking up. Many of its citizens are headed to work. Neither they, nor anyone else on planet Earth, are expecting a visitor, now approaching from outer space. A 20-meter-wide asteroid explodes above the city at an altitude of almost 30 kilometers. It releases the equivalent of 500 kilotons of TNT, or 20 to 30 Hiroshima bombs. Over 1,000 people are injured, most from falling debris and flying glass. Eerily, within 24 hours, another, even larger asteroid whizzes by Earth at a distance of 28,000 kilometers. That's within the orbit of our weather satellites.
An asteroid is a leftover building block from the formation of the solar system, and a few of them share the inner solar system with the Earth and will ultimately impact the Earth or Mars or Venus or the Sun. Asteroids that could impact the Earth are the greatest natural hazard we face, but the impacts are extremely rare. They are the extreme example of a disaster of low probability but high consequence.
Projectiles like these have been hitting our planet since the dawn of humanity, challenging us to explain. What are they? Where do they come from? Who sent them? Ancient observers turned to myth and legend for answers, describing them as omens, signs that something good or ill was happening in human affairs. In the spring of 44 BC, following the murder of Julius Caesar, the appearance of a comet was promoted as a sign of his ascent to godhood. We now know the annual Perseid meteor shower happens when Earth hits debris from the Swift-Tuttle comet. In ancient Rome, it was linked to Cleopatra's death and to the rescue of the Princess Andromeda by the warrior Perseus. Later on, scientists and philosophers who sought to refine their concepts of the universe struggled to explain these celestial objects. They saw the universe as a precision instrument, a cosmic clock designed by the ultimate watchmaker, God. They described a universe that moves in never-ending cycles. Planets circle the sun. The stars arc across the night sky. The seasons ebb and flow, all in beautiful harmony. This cosmic timepiece was a testament to the perfection of creation. In time, the idea of an intelligent designer gave way to the workings of natural laws. Our sun, we now believe, was born in the core of a vast cloud of dust and gas some 5 billion years ago. Within this solar disk, tiny particles glom together to form pebbles and rocks. Drawn by their mutual gravity, they merged into boulders and eventually small bodies called planetesimals. Such objects drew in gas and ice crystals to grow into the giants: Jupiter, Saturn, Neptune, and Uranus. The gravity of these gas giants caused countless icy bodies that enveloped the solar system to fly toward the sun, where they became comets. In the warm inner regions, rocky objects swarmed about. Some came together, merging or shattering in violent collisions, eventually growing into the rocky planets we know today. The collisions didn't end there. This is an elevation map of planet Mars. Heading north, we move over a vast lowland region, shown in blue. It's thought to be a scar left by a monumental impact early in its history that may have destroyed Mars' life-bearing chances. Planet Venus. A giant impact is one explanation for its extremely slow rotation. In the opposite direction, of all the other planets. Early in the history of our planet, a collision brought Earth perilously close to total destruction. A Mars-sized body crossed its path, slamming into it. The oblique angle of impact left Earth in one piece. Current theory holds that massive amounts of debris launched into orbit gradually came together to form the Moon. Over time, the presence of the Moon would stabilize Earth's rotation, while driving tides that helped pave the way for the emergence of life. That was only one in a long salvo of impacts.
Remember again that the asteroids are those remnants from which the planets formed. And while the planets were forming during that time, there were millions of times more asteroids than we see today, and they were raining down on our planet and growing our planet, in fact. All you have to do is look up at our moon today, and the cratered face of the moon, the very features that make the man on the moon, they are a tableau of those large, very much more numerous impacts that occurred 4.5 billion years ago when the planets were forming.
Craters that pock the lunar surface show the pounding that Earth must also have endured through its history. The solar system is still stocked with countless rocky objects, like those that pummeled the Moon and Earth. Over the eons, objects large and small have continued to strike the Earth. Most impact craters have long since eroded away. Others were obliterated by the rise of mountain ranges or by the reshuffling of continents. Some 200 left marks we can still see and ponder. Meteor Crater is one of the most striking. It dates back to a day, some 50,000 years ago, when the core of a busted-up asteroid slammed into what's now Arizona. Scientists believe the culprit was a nickel-iron mass 30 to 50 meters wide that weighed in at 300,000 tons. It left a hole 180 meters deep and just over a kilometer wide. This is the Pingualuit crater in Quebec, formed 1.3 million years ago. The impactor unleashed the energy of over 8,000 atomic bombs and left a crater 3.5 kilometers wide. The Manicouagan crater, known as the Eye of Quebec, was blasted out by a 5-kilometer asteroid 214 million years ago. It may have been part of a chain of impacts that struck in France, Ukraine, and North Dakota. It's reminiscent of a string of fragments from the Shoemaker-Levy comet that struck Jupiter in 1994. The largest known impact crater can be found in South Africa. At 2 billion years old, the Vredefort crater was created by an asteroid up to 25 kilometers wide. What you see here is the inner crater. It's set within a larger crater 300 kilometers across. It was part of a rare class of extra-large impactors capable of wreaking havoc all around the globe. Just recently, scientists discovered what appears to be an impact basin on the east coast of Antarctica. They proposed that shock waves from the impact set off the eruption of a giant volcanic hotspot on the planet's opposite side. Called the Siberian Traps, this volcanic eruption was responsible for the greatest mass extinction on record. Marking the end of the Permian period 260 million years ago, the devastation claimed 90% of all species on the Earth. Then there's the Chicxulub crater straddling Mexico's Yucatan Peninsula. It was created 65 million years ago by an impactor at least 10 kilometers wide. The debris thrown into the upper atmosphere would have enveloped the planet, blocking the sun.
I think the two most significant impacts that we've seen in Earth's history were the moon-forming impact itself, and then the impact 65 million years ago, a much smaller scale impact, but very significant from a human point of view, because that was the impact that wiped the world clear of the dinosaurs and 75% of all the other species of plants and animals on the planet at the time, and cleared the way for mammals to rise to prominence and for our own origin.
Coincidentally, a few million years later, another large asteroid blew a hole in Greenland. It's currently hidden beneath the Greenland ice sheet. The Hiawatha crater is the most recently discovered large crater. Objects like these were more numerous in the distant past. Over time, an estimated 99% of their total mass was pulverized in collisions, swept up in rising planets, or flung out of the solar system altogether.
We often see the asteroid belt depicted as this dense stream of rocks right up against each other, tumbling around in very close proximity to each other. And it's true that there are a lot of objects out there in this region between Mars and Jupiter, but they're not dense packed the way you often see them depicted. In fact, if you were sitting on or standing on any random asteroid out there in the main belt between Mars and Jupiter, you would never even by your naked eye be able to see the nearest asteroid to you. They just wouldn't appear that way.
Here is a map of all known asteroids up to the year 2018. The asteroid belt, shown in orange, is the largest concentration. To us, the most dangerous are the near-Earth asteroids, those shown in blue. They come within 1.3 times the distance between Earth and the Sun. In the last few decades, efforts to count and track them have led to a new sense of awareness that Earth may still be vulnerable. Today, the world's population is just under 8 billion people and could reach 11 billion by the end of the century. With so many of us now crowded into cities and coastlines, we struggle to shield ourselves from a range of natural disasters. Extreme weather, sparked by a warming climate. rising sea levels and floods, wildfires that now erupt with unknown fury, then there's the ever-present reality of war. With the threat of mass destruction and the displacement of millions of people. Can we address the ultimate threat? The one from space. 1998, Hollywood released 2 blockbuster movies.
Okay, gentlemen. Just hold on!
Armageddon. A comet is hurtling toward Earth. Astronaut heroes race out to blow it up and save the planet.
How's my time? Jam's up at 75.
Then, Deep Impact. This time, Earth doesn't get off so easy. That same year, 1998, in response to growing popular and scientific awareness of the asteroid threat, NASA began a long-term effort to discover and track them.
Only in Hollywood do asteroids capriciously change orbit and suddenly head for the Earth. The fact is they know Newton's laws and they follow them just fine. So when we do discover an asteroid, if we get good data, we can predict its orbit for decades or even centuries in the future.
Asteroid hunters have found around 30,000 objects, with 3,000 new ones identified each year. That includes an estimated 90% of the most dangerous, like the 10-kilometer rock that struck 65 million years ago. Our chance of being hit by one of these dinosaur killers is estimated at once every 100 million years. The chance of being hit by a 1-kilometer asteroid rises to once every 700,000 years. Moving down in size, 300-meter rocks should hit every 70,000 years, bringing continental-scale devastation. Smaller still, 140-meter objects hit every 20,000 years. And 40-meter objects like the one that punched a hole in Arizona every 300 years. A 40-meter object passes within the moon's orbit several times a year. The next size down, around 10 meters across, zips by about once a week. Scientists are seeking not only to identify these objects, but to clarify their trajectories and the chances they'll one day crash into Earth. Meanwhile, there are those that seem to come out of nowhere, like the one that hit Chelyabinsk in Russia. To scientists, it was more than just an ominous threat. 3.5 hours after it exploded, the polar-orbiting Suomi satellite began tracking the plume of dust and smoke. In an effort to learn more about the asteroid's physical properties, scientists followed the plume as it spread out in upper-level winds, forming a complete global belt. They further modeled the breakup of the asteroid, hoping to one day predict the atmospheric effects of incoming objects. The Chelyabinsk asteroid was reminiscent of the most famous asteroid impact in modern times. The Tunguska asteroid exploded over Siberia in 1908, leveling 2,000 square kilometers, including some 80 million trees. It took over a century for scientists to identify fragments of this impactor and to conclude that it was probably a comet. Ultimately, the best way to learn what these wayward bodies are made of and how their orbits can change over time is to pay one a visit. NASA launched the Dawn mission in 2007. Propelled by an ion-thrust rocket engine, Dawn entered the asteroid belt in 2011. Its targets: a large rocky body named Vesta, and the crown jewel of the asteroid belt, an icebound dwarf planet called Ceres. Together, they comprise over 1/2 of the total mass of the asteroid belt. Today, Vesta is pocked with craters, dark spots, and streaks, scars left by collisions with other asteroids. Some gully-like features may be the unlikely erosion marks left by flowing water. Vesta appears to have been whittled down by collisions. In fact, scientists have concluded that many of the asteroids that have flown by Earth were once part of Vesta. Not long after scientists began tracking and cataloging near-Earth asteroids, a team from the U.S. Air Force and the Massachusetts Institute of Technology discovered one that is now considered the greatest threat to Earth. The asteroid Bennu, represented in this NASA visualization, was named for a mythological Egyptian god. It was likely born in a collision of small planets in the inner part of the asteroid belt. With a diameter of some 500 meters, Bennu would inflict catastrophic damage if it hit Earth. And there is uncertainty about its path, which shifts over time due to the gravitational pull of planets, as well as the subtle pushing from solar radiation. The uncertainty of Bennu's path is one reason NASA sent a probe out to study it.
And liftoff of Osiris Rex, its 7-year mission.
In September 2016, the Osiris Rex spacecraft began a journey lasting 2 years and 3 months, covering a distance of about 2 billion kilometers. Within just a few days of its arrival, Osiris Rex was hit with a blast of particles flying off the asteroid. The blast did no harm, but it showed that Bennu is part of a rare class of active asteroids that regularly shed mass into interplanetary space. The spacecraft would spend almost 2 years circling Bennu while sending back images and mapping its surface. To the surprise of scientists on Earth, the asteroid is strewn with boulders. Over 200 of them are larger than 10 meters in diameter. The asteroid is essentially a loose pile of rocks and dirt held together by its collective gravity field. 60% of its volume is actually empty space. After a survey of potential landing spots, on May 10, 2021, the spacecraft maneuvered down to a tiny area devoid of large rocks. An onboard camera captured the descent. A device at the end of a long arm hit the surface, blasting dirt and small rocks into a collection device. the spacecraft hit its thrusters, to back out of the cloud of dust created by the blast, and to move away from the asteroid. After orbiting the asteroid, it began the long return flight to Earth. Osiris Rex will drop the sample container into the atmosphere for retrieval. Data from the mission has already allowed scientists to recalculate Bennu's trajectory. Fortunately, in its next pass by Earth, nearly 2 centuries from now, the chance of impact is set at just 1 in 1,750. Osiris Rex will go on to shed light on the path of yet another near-Earth asteroid. In the year 2029, 99942 Apophis, a slightly smaller asteroid, will pass within 32,000 kilometers of Earth. Here is its path compared to a sample of man-made satellites orbiting Earth. Once Osiris Rex drops off its Bennu samples, it will then swing back out to meet up with Apophis, just weeks before it races by Earth. It will spend the next 18 months orbiting the asteroid, mapping its surface, and studying the effects of Earth's gravity. With most large, highly destructive asteroids now identified, astronomers have begun to shift their search to smaller objects down around 50 meters across. Only 25% of them are currently known. What if one of these city killers took aim at Los Angeles? New York, London, or any of the world's great cities? Winds generated by the impact could claim 50,000 lives within seconds. Is such a destructive impact inevitable? There is a chance that someday we'll detect a giant boulder careening through space, large enough to survive the plunge into our atmosphere. How will we respond? Public awareness is our first line of defense. If you know it's coming, you might be able to get out of the way. That's why every June, the founders of World Asteroid Day implore citizens to pay attention and make planetary defense a priority. NASA, for one, has set up a new Planetary Defense Coordination Office to manage the expanding asteroid database and disseminate information to the public. In the U.S., the Federal Emergency Management Agency, FEMA, has begun to develop evacuation and public alert procedures. The next line of defense is detection. To avoid getting blindsided, we must monitor the sky for anything that moves. NASA has erected the Deep Space Network to communicate with spacecraft. That includes planetary radar to scan our solar neighborhood for Earth-bound objects. The agency runs the NEOWISE space mission to hunt for asteroids, as well as the Scout project, including a software system that projects their pathways. Atlas telescopes are scanning northern and southern skies. The new Vera Rubin Observatory will monitor a wide swath of the night sky, looking for stars exploding in distant space or asteroids and comets racing through the solar system.
The most scientifically interesting results of the last few years are a much more sophisticated understanding of orbits and how they change. a recognition, for instance, of what the astronomers call a keyhole, which means that there are some very sensitive points in an orbit. If it goes right precisely here, it'll come back and get you. If it misses by even a mile, it won't. And so we are understanding some of the details and subtleties of orbits. Obviously, it's not just a matter of discovering these objects with a survey, but making accurate predictions of their future path.
And liftoff of the Falcon 9 and DART.
Our third
on
line of
NASA's
defense:
first planetary
intercept
defense
and
test
neutralize
to
the threat.
intentionally crash into an asteroid.
Planetary defense is no longer just the subject of disaster movies. For a moment in September 2022, citizens of planet Earth turned their attention to an interplanetary spectacle. DART, the double asteroid redirection test, was sent on a 10-month journey powered by a small ion thrust engine fueled by solar energy. Racing in at almost 24,000 kilometers per hour, the DART spacecraft homes in on the binary asteroids Didymos and Dimorphos, 11 million kilometers from Earth. 10 days from the impact, the DART spacecraft releases the small secondary unit called LiCHA to record the action. Live streaming to Earth, DART's camera sends back 1 image per second. T-minus 1 hour. The asteroids are but a pixel of light. T-minus 20 minutes. Details appear on the larger asteroid Didymos. The smaller target, Dimorphos, is behind it. On approach, DART autonomously steers in the direction of Dimorphos. Two minutes to go. DART passes Didymos. Details on Dimorphos now become distinct. You can see that it's a rubble pile asteroid, similar to Bennu. Here is the last image, taken 2 seconds before impact. The rock in the center is close to 5.5 meters wide. From Earth, the Atlas telescope catches a cloud of rock and dust flying off the asteroid. Meanwhile, LiCHA, the Hubble Space Telescope, and the James Webb Space Telescope each record the blast. A week later, in the wake of the impact, the SOAR telescope in the Andes Mountains catches a 10,000-kilometer comet tail of dust and rocks accelerating away from the asteroid. Scientists expected the impact might shorten the asteroid's almost 12-hour orbit by at least 73 seconds. DART, the tiny interplanetary battering ram, managed to cut it by 32 minutes. With enough warning time, we can defend against small-sized asteroids like Dimorphos. Will this work with an asteroid 3 times larger, such as Bennu? And what'll we do if the asteroid appears suddenly, with little warning? One answer: follow the script of Armageddon or Deep Impact and nuke it. A group of scientists at the Los Alamos National Laboratory tried to find out how feasible this is by simulating a nuclear strike in a powerful supercomputer. Their study target? A 330-meter-wide, potentially hazardous, near-Earth asteroid called Itokawa. A Japanese mission found that it, too, is a conglomerate of dense rocks. On its surface, scientists planted a virtual 1-megaton nuclear bomb, 6 times more powerful than Hiroshima. In the first 30 milliseconds, a shockwave races through the rocks. Most of the fragments are too small to survive the plunge through Earth's atmosphere. However, the explosion risks showering the planet in deadly radiation. A recently published plan offers another solution. Sometime in the future, a large asteroid is spotted on a beeline for Earth. A robotic probe is sent out to survey it. Seeing through the dirt and gravel that lines its surface, the probe reports that it's a collection of boulders, some larger than a house. We turn to our last line of defense. A last-ditch effort to save civilization. Like an iron dome for planet Earth, we've stationed a robotic asteroid hunter on the surface of the Moon. As the asteroid bears down on Earth, astronomers use radar to track it. At a critical moment, they activate the system. It doesn't take much power to escape the Moon's gravity. With its near-Earth mission, the spacecraft can travel light on fuel, but heavy on firepower. After decades of experiments in tracking and maneuvering in space, Planetary Defense finally has its first test. The asteroid is still half an Earth away. The spacecraft is actively tracking it, computing its speed and trajectory. The target is approaching at over 1,000 kilometers per hour. Earth impact is all but certain. In this new age of planetary defense, nuclear bombs have been ruled out. But a single conventional explosive is not enough to destroy an asteroid. So instead, the spacecraft packs an arsenal. It fires a series of projectiles to meet the asteroid and soften it up. One charge penetrates, another explodes. Then, the final impact. Observing from Earth, scientists and the public, with their fate hanging in the balance, can only wait and hope. With any luck, those fragments that hit Earth are small enough to burn up in the atmosphere. Will we live another day? To strive, create, to wonder, and survive.